I spent over 80 years keeping secrets that few Britons know and that almost no history book mentions. I worked as a technical sailor in a facility that, officially, didn't exist. It was a factory hidden beneath a hillside in southern England, a place where the first prototypes of long-range torpedoes used in World War II were designed, assembled, and tested. For decades, I repeated the same answer whenever someone asked what I did. Just naval maintenance. But now, at the end of my life, I feel I can, and must, tell how that subterranean world of steel, steam, and absolute silence really worked. I was 19 when the Royal Navy sent me a message requesting my presence at an administrative office in Portsmouth. At the time, I believed it would be a routine reassignment, perhaps another technical duty aboard a destroyer. Instead, I entered a quiet room occupied by two officers I had never seen before. They asked me to sit, closed the door, and placed a sealed envelope in front of me. The atmosphere was formal, almost solemn, and although no one said so directly, I sensed that declining whatever waited inside was not an expected option. The senior officer explained that the Navy was forming a specialized group of personnel with mechanical aptitude and a record of discipline. According to him, I had been selected based on my maintenance reports, my performance during training, and my ability to follow procedures without improvisation. He emphasized that the assignment would not involve direct combat and that the work would contribute to long-term naval operations. Only after this introduction was I allowed to break the seal of the envelope. Inside, the briefing described a place identified only as Facility H-17. No region, no map, no indication of what I would repair or operate. The document mentioned research, engineering support, and strict confidentiality. A final line stated that I would be prohibited from discussing the project for an indefinite period, even with family members, instructors, or fellow sailors outside the assignment. I remember looking up and asking what exactly H-17 was. Both officers exchanged a look that made it clear the question would not be answered there. They told me that if I accepted, transportation would be arranged within 48 hours, and that my naval records would list me only as reassigned to special mechanical duties. They reiterated that nothing about the position violated military law or procedure, and that I would not be placed in unsafe conditions. Still, the secrecy surrounding the role carried a weight I did not fully understand at the time. I signed the acceptance form because I trusted the Navy, but I felt the pressure of a responsibility I could not yet define. When I left the room, the corridor seemed unusually silent. I walked back to the barracks with the envelope pressed against my chest, rereading the authorization letter without learning anything new from it. Several sailors asked where I had been, but the instructions were clear. I was to say nothing. That night, I barely slept. I tried to imagine the nature of a project so classified that it did not even receive a location on the memo. I thought of radar systems, engine research, or perhaps maintenance of new ship components. Nothing I imagined matched the truth I would eventually discover. 2 mornings later, before sunrise, I reported to a designated checkpoint near the docks. Instead of being taken to a ship, I was placed in a covered truck with 2 other sailors, both silent and clearly just as uninformed as I was. None of us exchanged questions, because the presence of the escort sitting across from us made it clear that questions would not be answered. We drove for hours through roads I did not recognize. Whenever I tried to track direction by the angle of the light or the sound of nearby towns, the truck would slow or change course, as if intentionally breaking any sense of orientation. Eventually, we stopped on a narrow road bordered by dense trees. The escort opened the doors and instructed us to step out. In front of us stood what appeared to be an ordinary wooden cabin, the type used by forest rangers. Its simple design made it look abandoned, but the 2 guards standing beside it revealed that this was no ordinary structure. One of them asked for our names and checked them against a list. Only then did he open the cabin door and lead us inside. The interior contained little more than a small desk and a single metal hatch built into the floor. The guard lifted the hatch, revealing an industrial elevator shaft descending into darkness. He told us that from the moment we stepped inside, we would follow the instructions of the personnel below and maintain confidentiality about all operations. The seriousness of his tone left no room for doubt. As the elevator descended, the wooden cabin above disappeared from sight, replaced by layers of reinforced concrete. At that moment, for the first time, I understood that this place had been designed to stay hidden not only from the enemy, but from most of our own military structure. When the elevator finally stopped, the doors opened to reveal a long corridor lined with pipes, machinery, and bright overhead lamps. A sign on the wall read, H-17 Engineering Division, Restricted Entry. A lieutenant greeted us and welcomed us to the facility. He explained that we had been selected for an assignment related to advanced naval engineering, particularly technology intended to extend the operational range of maritime equipment. His explanation was precise but avoided specifics, yet it was enough to make clear that the work conducted there was part of a larger effort to prepare the Navy for long-term maritime strategy. Nothing he said broke secrecy guidelines, but everything he said confirmed that we had entered a world with layers of confidentiality beyond anything I had imagined. Walking down that corridor for the first time, hearing the distant hum of machines and seeing technicians in uniforms different from ours, I felt the full weight of what I had agreed to. I had been chosen to participate in something hidden beneath the surface of the country itself. I did not yet know that this place would become the center of one of the most significant engineering efforts of its era. All I knew was that my life had just shifted onto a path that would remain invisible to the world for decades. When I first stepped out of the elevator and walked deeper into the main corridor of H-17, the scale of the facility became apparent in a way no briefing could have prepared me for. The air carried the scent of oil, metal, and circulating ventilation systems, a clear sign that the space had been carved and reinforced with long-term use in mind. Although the structure was hidden beneath a wooded hill, the engineering behind it was impressive for the era. Thick cables ran along the ceiling, connecting laboratories, workshops, and storage rooms. Every door we passed featured a coded identification plate, suggesting layers of access far beyond our initial clearance. A petty officer escorted us through the hallway, maintaining a steady pace that discouraged any attempt to linger or examine details. He explained that H-17 operated under the authority of the Admiralty's Directorate of Torpedoes and Mining, although the name itself was never spoken aloud within the complex. The official designation was simply the Directorate, a term used to maintain internal security. He told us that only a select number of engineers, machinists, and naval technicians knew of the facility's existence, and that its infrastructure supported projects considered essential for maritime strategy throughout the conflict. The specificity of his wording suggested that great effort had been invested into creating this environment of careful communication. As we moved forward, I heard the steady rhythm of machines operating behind walls. Compressors, testing devices, and mechanical tools. The vibrations under the floor indicated that the facility extended much deeper than the level we were on. The petty officer mentioned that its foundations had been expanded over the years to accommodate new research areas. None of this information compromised security, yet it conveyed the scope of the operation. Although he avoided naming exact projects, he emphasized that our work would focus on propulsion and mechanical reliability for equipment intended to function at long distances in maritime environments. We were led to a room designated as our briefing chamber. Inside stood metal benches, a chalkboard, and a map of the British coastline without markings. A lieutenant engineer entered and introduced himself as our training supervisor. His presentation outlined the structure of the facility: an engineering division, a materials and metallurgy sector, a propulsion laboratory, and a testing range located in an underground water channel. He explained that each division operated independently, and personnel were assigned to specific sections based on skill, not rank. The system ensured that information remained compartmentalized, a standard procedure in high-security projects. After the briefing, we received our identification tags. Mine bore only a number and a small symbol representing our division. The lieutenant made it clear that the tags were not to be shown outside the facility and were to remain on our uniforms at all times while inside. The tags controlled door access and recorded work hours through mechanical stations that logged entry and exit. These measures were designed not only for security, but also to track maintenance procedures with precision, as any error in the development of long-range naval equipment required complete traceability. Our guide then showed us the quarters where we would stay during active shifts. The sleeping area consisted of narrow bunks arranged in rows, with lockers for personal belongings. Conditions were modest, but clean. The lieutenant reminded us that while shifts could be long, the facility maintained strict schedules to prevent fatigue from affecting the accuracy of technical work. The emphasis on procedure and stability reflected how critical consistency was to the research conducted there. The dining hall was equally simple, offering a quiet space where personnel rarely discussed their tasks. Conversations revolved mostly around families, weather, or sports, never about operations. This unspoken rule became natural within days. Even those who had worked there longer maintained the same discipline, treating silence about the project as part of the job's foundation. Later that day, we were brought to the observation platform overlooking the engineering floor. From above, we could see long metal tables, precision instruments, drafting boards, and assembly rigs. Technicians in protective uniforms worked with careful, deliberate movements, measuring components and adjusting fittings. Although I still did not know the exact purpose of the equipment, I recognized the shapes of small propulsion units and guidance mechanisms typically associated with naval research. The designs were more advanced than anything I had encountered while serving on standard vessels, and their construction required patience and close attention to detail. The lieutenant described how every component went through several verification steps before reaching the testing area. Reliability, he said, was not simply an objective, it was the core philosophy of the facility. The room felt both distant and familiar, like a version of the naval workshops I had trained in, but refined into a precise and controlled environment. I understood then why individuals were selected so carefully. The facility demanded technical discipline, but also a temperament capable of working under confidentiality without hesitation. After the tour, we were allowed to walk the primary corridor, escorted by a supervisor. This final step helped us familiarize ourselves with the layout, while ensuring we did not access unauthorized sections. The deeper we moved, the more I realized how complex the underground structure was. Reinforced supports lined the ceilings, ventilation shafts carried filtered air through the chambers, and insulated pipes ran alongside the walls to regulate temperature in areas requiring stable conditions. Everything was interconnected, yet every corridor had controlled access points. When our shift ended and we prepared to return to the quarters, I paused for a moment to absorb the reality of where I stood. Above our heads, the forest and the hillside concealed an entire network of research designed to operate unseen. The facility did not appear on any surface map, had no public entry, and left no visible trace of the work that occurred within. To the outside world, the mountain was nothing more than part of the countryside. To us, it was a self-contained system where engineering, secrecy, and responsibility converged. That night, as I settled into the bunk assigned to me, the weight of the day lingered. I understood that H-17 was not merely a location, it was a world built to remain hidden, functioning silently for the sake of future operations at sea. And although I still did not know the full extent of its mission, I knew with certainty that whatever happened next would shape not only my life, but a chapter of naval history that few would ever be aware of. Life inside H-17 followed a rhythm unlike any naval assignment I had experienced. Days were measured not by sunlight or tides, but by the steady hum of ventilation systems and the precise timing of mechanical clocks mounted along the corridors. The lack of windows created a strange sense of detachment from the outside world, and soon I learned that it was intentional. The facility operated on the principle that focus increased when the mind was not tracking the passage of day and night. It took time to adjust, but eventually I found myself working according to the internal environment rather than the natural one. Our first full week was dedicated to orientation across the various sectors of the complex. We learned how air was filtered, how water flowed through the testing channels, and how each division maintained communication through a system of coded messages rather than open radio. Nothing in the facility relied on unsecured transmission. Even simple maintenance reports were delivered through sealed containers passed between stations. The system may have appeared excessive to an outsider, but within H-17, it was simply part of normal procedure. My assigned sleeping quarters were in a section known as Block C, located near the engineering workshops. The space consisted of 2 long rooms connected by a narrow passage, each lined with bunks and lockers. Privacy was limited, but the environment remained calm due to strict rules governing noise and movement. Lights dimmed at scheduled hours, conversations ended early, and even during rest periods, most of us conserved energy. We all understood that precision in our tasks depended on maintaining a clear and rested mind. Meals were served in a modest canteen, where the cooking staff operated with the same discipline shown in the technical areas. The menu rarely changed, but the food was filling and consistent. During these meals, I began to notice the unique culture that had developed among the personnel. There were no loud stories, no speculation about missions, and no rivalry between divisions. People spoke quietly about their families, letters received from home, or memories of life outside the facility. Any mention of equipment, research, or procedures ended immediately. Everyone honored the boundary between personal conversation and classified work. The workstations where I received my training were carefully arranged to maximize order. Each bench had a set of calibrated tools, spare components, and instruction logs. My supervisor, a chief technician with decades of mechanical experience, emphasized the importance of recording every detail. Even a minor adjustment required documentation. He told me that reliability in long-range naval equipment depended not only on design, but on the ability to reproduce results exactly. The workshop's atmosphere reflected that mindset: clean, organized, and consistently monitored. One of the most surprising aspects of living in H-17 was the absence of pressure in direct communication. The facility demanded accuracy, but never rushed decision-making. Supervisors encouraged questions and insisted that no component should advance toward testing until all personnel confirmed it met specifications. This approach contrasted sharply with the hurried repairs I had witnessed on active vessels, where time constraints shaped every action. In H-17, time existed to serve precision. I eventually understood that this environment produced equipment with reliability far beyond standard field conditions. Our days also included scheduled training sessions in a classroom located near the central corridor. Here we studied propulsion principles, metallurgy, and the changes in naval strategy that had prompted the creation of H-17. These lessons explained that long-range technology had become essential for protecting convoys, countering enemy submarines, and improving the Navy's ability to operate far from home bases. Although the instructors never referenced specific operations, their explanations provided enough context to understand why secrecy was considered vital. The success of these technologies depended on maintaining an advantage, and that advantage required silence. Despite the intensity of the work, the facility maintained a sense of routine that prevented fatigue. Breaks were strictly enforced, and personnel rotated through tasks to avoid monotony. Even so, the isolation beneath the hillside had an effect on many of us. Without natural light, weather, or the sounds of daily life, time seemed to stretch. Letters from home became our primary connection to the world above. Mail delivery occurred weekly, supervised closely, and inspected only for security, never for personal content. Receiving a letter created a sense of relief that balanced the isolation. During off hours, some personnel gathered in the small recreation room, where a radio tuned only to approved broadcasts provided music and news that contained no operational detail. Others used the quiet hours to read or write. I often walked the central corridor, stopping near the reinforced door that led to the testing area. The faint echo of water flowing through the underground channel reminded me that directly beneath the concrete lay one of the most important engineering assets of the facility. Even without seeing the tests myself at that early stage, the sound carried a sense of purpose. Although life underground might seem restrictive, the environment gradually became familiar. The consistent schedule, the professionalism of the staff, and the knowledge that our work served a critical role created a sense of unity. By the end of my first month, I no longer questioned the necessity of the facility's secrecy. The routine had become part of me, and the isolation transformed into focus. I knew that whatever was being developed in the deeper sections of H-17 would soon demand even greater accuracy, and I felt prepared for it. Yet even with this growing comfort, a sense of anticipation remained. Everyone knew that at some point we would be introduced to the core project of the facility. The supervisors provided hints through their emphasis on precision and documentation, but none of us had seen the full designs. The atmosphere inside H-17 was not one of mystery, but of measured preparation, as though all of us were being trained for a task that required complete understanding of our environment before we could take the next step. I went to sleep each night in Block C, with the hum of machines echoing faintly through the walls. It was a constant reminder that while we rested, the work of H-17 continued. The facility never slept, not even for a moment. Its existence depended on continuous operation, and we were part of that system. Life beneath the surface was unlike anything I had imagined, but it shaped my discipline in ways that would define every moment that followed. The day I first saw the prototype workshop of H-17 marked a turning point in my understanding of the facility's purpose. Until then, my tasks involved maintenance routines, inspections of mechanical tools, and training sessions that prepared us for precision work. But when the supervisors finally allowed us to enter the central assembly hall, I realized that everything we had learned so far existed to serve a single, highly specialized objective. The workshop was larger than any engineering space I had worked in before, with rows of reinforced tables, overhead cranes, and storage racks filled with carefully labeled components. The air carried the quiet tension of a place where every action mattered. At the center of the room lay a long cylindrical structure resting on stabilizing mounts. At first glance, it resembled the general shape of a naval device used for underwater operations, but its length and complexity suggested a different scale. A senior engineer approached us and explained that we were looking at the early versions of long-range propulsion units being developed to expand the operational reach of maritime equipment. His explanation didn't mention specific models, but anyone with mechanical experience could recognize the evolution from earlier British designs. The innovations focused on fuel efficiency, stability, and navigation control, areas the Navy had been eager to advance. The engineer described how previous models used during the early years of the war had limited endurance, restricting their ability to operate effectively at long distances. This limitation had encouraged the development of improved propulsion systems capable of maintaining speed and direction for extended periods. To achieve this, the prototypes required significant changes in internal layout, including more efficient combustion chambers, redesigned propeller assemblies, and enhanced gyroscopic stabilizers. Each modification had to be tested repeatedly, not only for performance but also for consistency, since reliability was essential in long-range maritime operations. Once our supervisor saw that we understood the general purpose of the prototypes, he assigned us to stations responsible for handling specific components. My first task involved calibrating small mechanical regulators that controlled the flow of fuel into the combustion chamber. These regulators were delicate and required precise adjustments. A difference of even a fraction of a millimeter could affect the entire system. I learned to measure, adjust, and remeasure every detail. Over time, this attention to detail became second nature. Working alongside the engineering team, I witnessed firsthand how each prototype passed through multiple stages of development. Early versions often required complete redesigns because the components could not maintain the required endurance. Later versions gradually improved, with adjustments informed by calculations, controlled tests, and the experience of senior technicians. The process was methodical rather than rushed. Our supervisors insisted that understanding why a modification worked mattered more than completing it quickly. The assembly hall maintained a strict environment. Conversations were kept brief and focused solely on technical matters. Any question not directly related to the project was deferred until break periods. Engineers and technicians from different divisions coordinated through written logs to maintain consistency across shifts. Every action had a corresponding entry in the documentation, ensuring that the development process remained traceable at all times. Despite the intensity of the work, the environment fostered cooperation. If a component failed during testing, no one blamed the individual handling it. Instead, the team reviewed the steps that led to the failure, identifying adjustments for improvement. This method reflected the philosophy of H-17. The project's success depended on collective accuracy. Each task contributed to a larger system of reliability. One of the supervisors showed us the stabilizing mechanism that helped maintain direction during long-distance travel. Unlike earlier devices that relied heavily on operator input, this system used a refined gyroscopic unit. It corrected minor deviations automatically, ensuring a consistent trajectory. The principle was not new, but the level of improvement was significant. The team had spent months adjusting the unit's sensitivity to achieve the level of stability needed for extended operation. As the weeks passed, we observed more advanced prototypes arrive in the assembly hall. These versions incorporated stronger materials and refined internal structures. Their outer shells were reinforced with alloys selected for durability and predictability under stress. Each improvement demonstrated how much the facility had learned from earlier attempts. By then, I could recognize the distinct sound of the fuel systems when technicians performed controlled ignitions in isolated test chambers. The hum of the motors was smoother each time, signaling progress. One important aspect of our work involved cleanliness and controlled conditions. Even small particles of dust or oil residue could interfere with internal components. The assembly hall followed strict cleaning routines, and personnel wore protective gear to prevent contamination. Tools were inspected before each use, and components were stored in sealed containers when not being assembled. This level of care felt unusual at first, but soon it became an essential part of the process. The defining moment in my early months at H-17 came when we assisted with the preparation of a prototype destined for a limited performance test. Although the test itself would be conducted in another section of the facility, our role in ensuring the prototype met every specification was clear. The atmosphere in the workshop grew more focused than usual as technicians performed final checks. The senior engineer reviewed each part, confirming alignment and stability. When the prototype was finally taken from the assembly hall, I felt a sense of accomplishment I had not expected. Even though the project remained hidden from the outside world, our work contributed to an achievement that represented a significant advancement in naval engineering. By the time I returned to my quarters that evening, I understood the importance of the task entrusted to us. We were not simply assembling machinery. We were participating in a process that would redefine maritime operations. The prototypes we built in that underground facility represented the beginning of a new phase in naval capability, one that would influence long-range strategy for decades to come. Black and white photo, realistic style, depicting a WWII European setting, 1940s Germany or France, abandoned railway stations, freight wagons, and war-torn villages. Moody lighting, high contrast, historical accuracy in clothing and vehicles, soldiers in period uniforms, civilians in 1940s attire, dusty streets, overgrown tracks, tense atmosphere, cinematic composition, film grain, photorealistic, no color, authentic WWII look. I remember the first morning I was allowed inside the operations wing, the part of the factory most workers never saw. It stood behind a steel door marked with a simple code, nothing dramatic, but everyone knew the weight behind it. Inside, the air felt colder, almost deliberate, as if the walls themselves insisted on discipline. This was where the long-range torpedo program received its final approvals, where each mechanical choice and each safety test was reviewed in near-ritual fashion. I walked there as a junior naval technician, unsure if I deserved a place among those who had already shaped the war from behind closed doors. The heart of the operations wing was a narrow room lined with drafting tables and large boards showing torpedo performance logs. Engineers and officers gathered there to interpret every deviation, no matter how small. When I first stood among them, I noticed that no one raised their voice. Every discussion carried a careful tone, as if a single incorrect assumption could echo all the way to the North Atlantic and cost lives. The British Admiralty maintained strict oversight, and each of us felt the responsibility. What made long-range torpedoes so different was their dual nature. Part delicate instrument, part engine of immense force. The early electric propulsion systems, which we handled with protective gloves, required absolute precision. Even a minor imbalance in the gyroscope or a tiny flaw in the battery casing could lead to failure. We tested the propulsion units repeatedly in small, sealed chambers designed to simulate pressure changes. Some tests lasted hours, others days, and we were expected to record everything with precision. Those notebooks still exist somewhere, though many names written in them have been forgotten. I learned quickly that secrecy shaped every moment of our routine. We were never told the location of the submarines that would eventually use our torpedoes, nor the operations planned for them. Our duty was limited to manufacturing, calibration, and verification. Still, I could not avoid imagining the scenarios. I knew German U-boats were hunting convoys relentlessly, and I understood that the weapons we built would be crucial for the Royal Navy's ability to respond. That awareness settled over every test I conducted. One of the tasks assigned to me involved monitoring the guidance mechanism. It was a fragile assembly, relying on gyroscopic stability to maintain a true course even at long distances. Early versions sometimes veered off by several degrees during water tank trials. To correct this, engineers introduced redesigned vanes and delicate balancing weights. I spent long hours adjusting them with a miniature wrench, convinced that each correction, no matter how small, might later influence a battle I would never witness. When my supervisor checked my work, he always reminded me that precision saved sailors, while shortcuts endangered them. It was a principle repeated constantly, but never lightly. The water tank testing area was one of the few parts of the factory that vibrated with activity. The tank itself was enormous, stretching across the room like an indoor canal. We placed the torpedoes on a rail system that slid them smoothly into the water. Observers watched from above, marking any wobble or deviation. The sound of the motor activating underwater created a deep hum that resonated through the walls. I often stood at the edge, recording revolutions and temperature readings with cold fingers. Even during long shifts, the reverberation of the tank made it impossible to forget what we were building. But the tests were not always smooth. I remember one trial in which the torpedo stalled halfway through the tank, its motor fading unexpectedly. Engineers rushed to retrieve it, their boots splashing on the metal walkway. The problem turned out to be a small crack in the insulation of a cable, caused by a manufacturer who had unknowingly supplied a flawed batch. The discovery led to an immediate recall, and every relevant component was checked again. Moments like that reinforced the philosophy that governed the factory. Nothing was left to chance. Strict supervision was constant. Officers from the Admiralty visited frequently, reviewing our logs, asking questions that were always direct and never casual. They wanted to know why a propulsion unit heated too quickly, or why the gyro drifted slightly on a particular model. No one dared provide vague explanations. If we lacked an answer, we said so clearly and returned to find it. Their presence acted as a reminder that the entire operation existed to support sailors scattered across the oceans, most of whom would never know who built the tools they depended on. Despite the pressure, camaraderie formed quietly among us. We seldom talked about our personal lives, but we shared the weight of responsibility. When someone solved a difficult issue, like adjusting the torque regulation to maintain stable acceleration, there was a subtle nod of respect from the others. We worked in shifts that blurred days into nights, especially during intense periods when reports from the Atlantic revealed increased attacks on merchant convoys. The more urgent the situation became, the more determined we were to ensure each torpedo left the factory in perfect condition. Occasionally, rumors spread among the workers about operations at sea. Though we never received official confirmation, we sometimes heard that a submarine had returned safely after engaging an enemy vessel. Such news stayed with us quietly, offering a reminder that our long hours had purpose beyond the walls of the factory. Yet we were careful not to speculate too openly. The culture of secrecy was strict, and even innocent conversation could be misinterpreted. We kept our focus on the work. By the end of my first year in the operations wing, I began to understand that the factory functioned like a living organism, its rhythm shaped by war, but driven by the discipline of thousands of ordinary workers. Every component we touched traveled a long chain before reaching the sea. That chain relied on commitment, accuracy, and an unwavering belief that careful work mattered. For me, Chapter 5 marked the point when I accepted that our decisions, made quietly in a hidden facility, influenced events far beyond our sight. The deeper I went into the daily work of the torpedo program, the more I understood that our greatest challenges were not always mechanical. Much of what shaped the project came from the need to prove reliability through an endless cycle of tests, many of which pushed the torpedoes to their limits. These trials took place in auxiliary facilities around the main factory, each one designed to simulate conditions submarines faced at sea. I spent countless hours in those sites, watching machines stress every bolt, seal, and circuit until failure revealed itself. Only then could we correct the weakness. One of the most important test areas was the pressure chamber wing. It consisted of several cylindrical metal rooms capable of simulating the immense forces found at depth. The early long-range models required durable casings that would not deform or crack under pressure. Even a slight weakness could cause a catastrophic breach. We secured torpedo components inside the chamber, sealed the door, and increased the pressure slowly. Through a small window, reinforced with thick glass, we watched for distortions. Sometimes a tiny bead of condensation or a faint metallic groan signaled that a redesign was necessary. The pressure chamber never lied. It revealed the truth with cold precision. I remember one test particularly well. It involved a group of electric propulsion units designed for extended operation. They were intended to maintain speed for distances previously considered unrealistic. When the test began, the readings were steady, but after several hours, one motor showed a temperature spike. The spike grew rapidly, and alarms rang across the chamber controls. We shut the system down and later discovered the issue came from a microscopic flaw in the cooling channel. Had the flaw gone unnoticed, it could have compromised an entire mission. The engineers who resolved the problem worked through the night, adjusting the channel pathway before presenting the improved version the next morning. Another area where we spent considerable time was the vibration testing hall. Torpedoes experienced strong oscillations during launch, and if any internal component shifted even slightly, the guidance system could become unreliable. The hall contained mechanical platforms that shook components at controlled frequencies. I held on to the railing more than once as the entire floor vibrated with such force that it felt like an engine room on a ship. The tests produced a low thunder that echoed through the walls, and we inspected every unit afterward, checking that screws had not loosened and sensitive instruments had not drifted out of alignment. Our work required methodical calm, even amid the constant shaking. One of my most meticulous assignments was to document the stability analysis of the gyroscopic units. These devices were central to maintaining a straight course, particularly in long-range torpedoes. Small variations in temperature or humidity could cause subtle changes in balance. We conducted stability tests inside a climate-controlled chamber, where the air could be adjusted to conditions similar to the North Sea, the Mediterranean, or the colder Arctic waters. As temperatures shifted, I monitored rotational data, watching for the slightest deviation. Any inconsistency required recalibration, and recalibration demanded absolute focus. I sometimes spent entire nights turning a fine adjustment screw a fraction of a millimeter at a time. Beyond mechanical reliability, safety tests were equally rigorous. War demanded effective weapons, but the British government insisted on strict internal procedures to reduce the risk of accidents inside the factory. All explosive components were handled in separate buildings with reinforced walls and carefully maintained humidity levels. Although my role focused on propulsion and guidance, I occasionally accompanied safety officers to inspect these areas. We observed workers wearing specialized gear, following protocols designed to minimize friction or static. The atmosphere was quiet and disciplined. No one rushed. Everyone understood that caution protected not only the factory, but also the workers' families. Another significant component of our testing involved range simulations. While full-distance trials at sea were conducted by naval units, we performed scaled simulations in controlled pools. Engineers calculated drag coefficients, energy consumption rates, and acceleration curves. We repeated tests until the performance logs exhibited stable patterns. I often found myself reviewing these logs for hours, comparing them with previous models to understand how improvements in propulsion translated into extended distance. The sense of progress was steady, but never taken for granted. The war created urgency, but it did not erase the need for ethical responsibility. Every test was governed by strict oversight from the Ministry of Supply. Inspectors ensured that our processes respected safety requirements. These guidelines protected both the workforce and the broader environment. Even the disposal of materials, such as old batteries or damaged casings, followed set procedures. It was a system designed not only to support the war effort, but also to prevent unnecessary harm. I respected those rules deeply, and they shaped my understanding of accountability. One of the most challenging tasks I faced during Chapter 6 of my journey involved endurance analysis. Long-range torpedoes required energy storage systems capable of functioning reliably across extended distances. The batteries used were advanced for their time, and each unit underwent repeated charge and discharge cycles. These tests took days, sometimes weeks. I monitored voltage stability, heat output, and endurance curves. When a battery failed prematurely, we documented the cause and returned the unit for redesign. Some nights, I slept in a small cot near the testing area, waking every few hours to record data. The work was demanding, but it offered a quiet satisfaction. Each hour contributed to safer and more dependable performance. By the time this chapter of my service unfolded, I had grown accustomed to the rhythms of the testing regime. The factory no longer felt like an isolated building, but a system connected to the broader war effort. Every test represented a link in a chain that extended far beyond us. When we approved a unit, it traveled onward to assembly, then to the Navy, and eventually to submarines patrolling distant waters. That understanding never left me. In the end, the testing process forged not only better torpedoes, but a stronger sense of duty among all of us involved. We learned that precision required patience, and reliability demanded discipline. Each successful test reflected countless hours of concentrated effort. We worked not to seek recognition, but because sailors depended on us. It was a truth that shaped every decision we made, and it defined the meaning of our service inside that hidden British factory. Black and white photo, realistic style, depicting a WWII European setting, 1940s Germany or France, abandoned railway stations, freight wagons, and war-torn villages. Moody lighting, high contrast, historical accuracy in clothing and vehicles, soldiers in period uniforms, civilians in 1940s attire, dusty streets, overgrown tracks, tense atmosphere, cinematic composition, film grain, photorealistic, no color, authentic, WWII look. As the war intensified, the factory's role expanded beyond simple production. What had once been a secret manufacturing site became the center of a complex network of scientists, naval officers, intelligence specialists, and civilian workers, whose cooperation shaped the evolution of long-range torpedoes. By the time I reached the middle of my service there, I began to understand that our success relied not only on machinery or engineering talent, but on a system of partnerships conducted behind closed doors. These relationships were rarely spoken of publicly, but they influenced nearly every decision we made. One such partnership involved the Admiralty's technical division. Officers visited regularly to discuss operational needs from the front lines. They brought reports from submarine crews who had launched earlier torpedo models and observed their behavior in battle conditions. These visitors explained how changes in ocean temperature could affect propulsion, how currents influenced guidance accuracy, and how enemy vessels adapted to British tactics. Their insights shaped the modifications we worked on daily. When they walked into the factory, their uniforms reminded us that our designs were not theoretical. They were instruments sailors would rely on far from home. Another crucial collaboration came from the scientific community. The Royal Navy sought help from universities and research laboratories across Britain. Physicists studied hydrodynamics, electrical engineers analyzed current flow through the improved battery systems, and metallurgists experimented with alloys capable of withstanding pressure without adding unnecessary weight. Some scientists worked on site under strict security measures, while others sent results through controlled channels. Their involvement accelerated breakthroughs that would otherwise have taken months or years. I often found myself standing beside researchers who spoke with a precision shaped by academia, and I listened carefully. Their theories translated into practical changes on our assembly lines. One of the most fascinating groups we worked with was the team responsible for magnetic influence fuses. These devices detected variations in magnetic fields to trigger detonation at the optimal moment. Their development required careful testing, as the early war years had revealed flaws that caused premature activation. Engineers specializing in magnetism studied how the Earth's field varied across different regions of the ocean. They adjusted the fuse designs accordingly, reducing the chance of malfunction. Their work demanded secrecy, and their sections of the factory operated under additional restrictions. I visited these areas only when necessary, and the atmosphere there was always one of focused intensity. During this period, intelligence officers also became more involved in our operations. They monitored the risk of sabotage and ensured that classified information remained contained. Some officers briefed us on potential espionage attempts targeting British weapon development. They never shared specific details, but they insisted on procedures that limited unnecessary access to sensitive areas. Every worker carried identification, and every movement was logged. Security checks became routine. At first, these procedures felt excessive, but with time, I understood their importance. A single breach could have endangered not only the factory, but the entire Royal Navy SS strategic advantage. Beyond official channels, the factory maintained working relationships with industrial suppliers. Long-range torpedoes required components sourced from multiple companies, each specializing in a particular area. Some produced precision bearings, others manufactured specialized battery plates, and still others forged casings from durable steel. To protect secrecy, suppliers shipped parts under coded instructions, often without knowing what the final product would become. Representatives occasionally visited to confirm quality standards, but they remained unaware of the complete picture. I found it remarkable how each piece, handled by individuals scattered across Britain, contributed to a device designed to operate silently under the sea. The human element in these partnerships shaped the atmosphere of the factory. With so many specialists moving through the facility, we witnessed a blend of perspectives. Naval officers spoke from experience, scientists from theory, and workers from practical intuition. Engineers bridged these worlds, translating ideas into functioning systems. I often acted as a mediator, carrying questions from the assembly team to a visiting scientist, or explaining a complex theory in simpler terms so a supervisor could adjust production steps accordingly. Communication became a vital tool, and we learned that clarity prevented errors that could compromise a torpedo's reliability. One of the most memorable collaborations occurred during the development of improvements to the guidance gyroscopes. A university-based physicist arrived with new research suggesting that temperature variations inside submarine launch tubes could affect the balance of the gyroscopes before firing. His claim challenged long-held assumptions, but our leadership encouraged him to demonstrate his findings. We set up controlled tests inside a thermal chamber, adjusting the temperature gradually while measuring gyroscopic drift. His theory proved correct, leading to subtle changes in insulation and calibration methods that significantly improved guidance accuracy. Moments like that reminded me how much we benefited from outside knowledge. As these partnerships expanded, the factory's workload increased. Meetings filled our schedules, and every new insight created a list of adjustments to evaluate. Some modifications required reworking entire batches of parts, while others introduced new checks in our testing routines. Although the pressure grew, it also deepened our sense of purpose. The war demanded adaptable solutions, and we provided them by combining our strengths with those of our partners. Each collaboration strengthened our resilience. Despite the secrecy surrounding our work, we developed a sense of unity with the individuals who contributed to the torpedo program. Even though many of them remained with us for only brief periods, their influence stayed with us long after they returned to their respective institutions. We learned to welcome new perspectives and to trust that cooperation, not competition, produced the most effective results. Looking back, I realized that Chapter 7 marked the moment when I fully understood the depth of the network supporting our efforts. The factory itself was only one part of a larger system, sustained by knowledge, discipline, and shared responsibility. No individual, no single department, and no isolated group could have produced the long-range torpedoes that shaped Britain's naval strength. It was collaboration, quiet, determined, and often unseen, that gave our work meaning and ensured that each device leaving our assembly lines carried the collective effort of countless minds committed to the same goal. As the war reached its most demanding years, the factory shifted into a rhythm that no longer resembled ordinary industrial life. Daytime production alone could not match the urgency of the Royal Navy's needs, and so the factory adopted a schedule that ran without interruption. I found myself increasingly scheduled for night operations, a phase of work that revealed a different side of the facility. The silence outside, the dim lights inside, and the reduced staff created an atmosphere that shaped some of my most vivid memories. Night work brought challenges that tested our endurance, precision, and discipline. Although security protocols remained constant regardless of the hour, the nighttime environment heightened our sense of alertness. Guards patrolled the perimeter with deliberate calm, their steps echoing across the concrete. Every gate and checkpoint operated with the same scrutiny as during the day. But the stillness made each procedure feel more intense. Inside, the corridors appeared lengthier, and the hum of machinery carried farther. It was during these hours that I became fully aware of how vast the factory was and how many hidden rooms, storage segments, and testing chambers remained active even when most workers slept. Night operations were assigned to experienced staff members who demonstrated reliability and attention to detail. Mistakes made under artificial lighting could be costly. Supervisors selected small teams for each section, ensuring that every shift had at least one technician capable of addressing unexpected complications. I was often assigned to propulsion diagnostics or gyroscope calibration. These tasks required concentration, and for that reason, some believed night hours actually improved accuracy. Without daytime noise or the constant movement of large groups, we could hear variations in motor pitch or detect faint vibrations that might otherwise be overlooked. The factory's power management system played a critical role during night shifts. Electricity demands rose sharply when multiple test platforms operated simultaneously, and engineers monitored consumption carefully to prevent overloads. During one shift, I recall a moment when a minor fluctuation caused the lighting to dip briefly. It lasted only a second, but every worker froze at their station. The light stabilized quickly, yet the incident reminded us of the fragility of even the most advanced systems. We reported the fluctuation, and by the next hour, electrical technicians inspected the transformers responsible for balancing the facility's circuits. Their swift response highlighted how well each department understood its role. Night shifts also played a key role in managing the factory's testing schedule. The pressure chambers, environmental rooms, and vibration stands operated continuously to keep up with demand. Long-range torpedoes required endurance tests that ran for hours, sometimes days, and night operations ensured that these analyses progressed without interruption. I often monitored temperature readings, battery discharge curves, and stability indicators while the rest of the world slept. There was a unique sense of responsibility in knowing that while only a handful of us remained awake, critical data continued to flow. Communication between day and night teams relied on detailed logs. Before leaving, the daytime crew documented every observation. We reviewed their notes carefully and added our own entries so the next shift could follow the work seamlessly. The accuracy of these logs mattered enormously. If a minor anomaly appeared in propulsion behavior, the note prevented the next technician from misinterpreting the cause. This simple system of written continuity kept the factory functioning like a single organism, even though hundreds of workers rotated through its halls. Despite the intensity of nighttime work, the factory leadership recognized the importance of maintaining workers' well-being. Meals were provided during long shifts, and designated rest periods allowed us to recover briefly. Though modest, these breaks helped us maintain clarity. I often sat with colleagues in a small canteen illuminated by soft overhead lights. We spoke quietly about our tasks, our families, or the progress of the war as far as we knew it. The conversation always circled back to our responsibilities. Even in quiet moments, the sense of duty never faded. One of the recurring challenges of night operations was the temperature inside the testing labs. With fewer people moving through the facility, the air grew cooler, and temperature-sensitive equipment reacted differently. In some rooms, we had to adjust environmental controls more frequently to maintain consistency. This was particularly important in the gyroscope chamber, where slight drops in temperature risked altering rotational balance. I became adept at anticipating these shifts and modifying the controls before any deviation affected our results. Safety remained at the forefront of every nighttime procedure. Although fewer workers were present, the handling of electrical systems, mechanical components, and propulsion units still required unwavering caution. Alarms and emergency response systems were tested regularly to ensure readiness. Every member of the night team understood evacuation routes and first aid protocols. Fortunately, incidents were rare, but the seriousness of our work demanded vigilance. The factory maintained clear guidelines that prioritized worker safety, and adherence to these rules ensured that operations remained stable and controlled. In addition to technical duties, night operations occasionally included interactions with visiting officers or inspectors. Because certain tests ran continuously, they arrived at unconventional hours to review data or observe procedures. Their presence reminded us that our work was always connected to the larger war effort. These visits often brought updates from naval missions, and while the information was limited, it reinforced the significance of our contributions. We knew our work operated in the background of a far greater struggle unfolding across the oceans. Perhaps the most defining effect of the night operations was the way they changed my understanding of endurance. Working under low light, maintaining concentration through quiet hours, and managing long stretches without seeing daylight required mental discipline. Yet these nights shaped me into a more capable technician. I learned to rely on precision rather than speed, patience rather than urgency, and methodical record-keeping rather than assumptions. These qualities became essential in the later stages of the program. As the war progressed, the importance of night operations only grew. Our torpedoes improved steadily, their range increasing, and their guidance becoming more reliable. Each night shift contributed to that progress. We were a small part of a vast effort, but we carried our responsibilities with pride. When I left the factory at dawn after a long night, the rising sun reminded me that the work continued. Day team members walked in with renewed energy, and I handed them the logs that captured the night's progress. The cycle never broke, and each passing day brought us closer to completing the mission we had worked so hard to support. In Chapter 8 of my service, I learned that the quiet hours revealed truths the daytime could not. The factory never slept because the war never paused, and neither did our commitment. Black and white photo, realistic style, depicting a WWII European setting, 1940s Germany or France, abandoned railway stations, freight wagons, and war-torn villages. Moody lighting, high contrast, historical accuracy in clothing and vehicles, soldiers in period uniforms, civilians in 1940s attire, dusty streets, overgrown tracks, tense atmosphere, cinematic composition, film grain, photorealistic, no color, authentic WWII look. By the time I reached the later stages of my work inside that hidden British factory, the long-range torpedo program had matured into a sophisticated operation. More efficient propulsion systems, improved gyroscopes, and refined casings had advanced the reliability of each new batch. Yet the sea remained the ultimate judge of our efforts. No matter how precise our tests were, no matter how carefully we calibrated each system, the ocean exposed flaws that no laboratory could fully predict. Chapter 9 of my journey involved confronting those truths through field reports, recovered components, and the accounts of sailors whose missions depended on the devices we created. Official test ranges at sea were conducted by naval crews with strict protocols. Submarines launched prototype torpedoes under controlled conditions, often at remote coastal sites to maintain secrecy. Engineers from our factory rarely participated in these trials directly, but we received detailed reports summarizing performance, behavior, and results. These reports arrived in sealed envelopes accompanied by technical notes. I often joined senior engineers to review the data, translating it into actionable adjustments for the manufacturing lines. One of the earliest patterns we observed involved the interaction between torpedo casings and unpredictable ocean currents. Even though our hydrodynamic tests in controlled pools provided consistent results, field trials revealed that certain currents caused subtle deviations in stability. These deviations were not catastrophic, but they influenced path accuracy over long distances. The issue was traced to variations in casing surface finish. Even slight irregularities increased drag. Our response required refining the polishing process, ensuring a smoother surface that interacted more predictably with water flow. The complexity of such a small detail reminded us how sensitive underwater travel truly was. Another challenge that surfaced during sea trials was battery endurance under low-temperature conditions. Deep waters, especially in northern regions, reduced battery efficiency more than expected. The cold slowed chemical reactions inside the cells, decreasing the torpedo's operational range. To address this, engineers modified insulation within the battery compartment and adjusted pre-launch warming procedures. These changes improved performance significantly. I recall feeling a sense of relief when later reports confirmed stable energy output, proving that careful modifications could overcome environmental obstacles. We also studied the behavior of guidance systems in open water. The gyroscopes, though highly refined, responded differently when exposed to the subtle vibrations of submarine launch tubes. Naval crews recorded slight deviations in the first seconds after launch, moments critical for establishing a straight trajectory. To mitigate this, we reinforced the initial stabilization mechanism and enhanced mounting structures. Adjustments like these highlighted the importance of real-world feedback. No mechanical system, no matter how well built, behaved exactly the same in every environment. One of the most striking moments of my service occurred when fragments from a test torpedo were returned to the factory. The device had been recovered after a controlled detonation demonstration. The casing pieces were bent and charred, but still intact enough for analysis. Holding those fragments in my hands made me realize how the machines we worked on every day underwent extreme conditions at sea. The recovered metal showed patterns of stress that matched our predictions, confirming that the reinforced alloy used for the newer models performed as intended. It was a tangible reminder of why every calculation mattered. Communication between the factory and the Admiralty grew more frequent during this phase. Naval officers visited to discuss improvements based on operational feedback. Their presence brought a weight of responsibility. They described conditions aboard submarines, tight quarters, constant tension, and the need for dependable equipment. Hearing those accounts directly from the people who relied on our work deepened my understanding of the consequences of failure. A miscalculation, even a small one, could place crews at risk during missions in hostile waters. Another aspect of sea-based evaluation involved acoustic behavior. Long-range torpedoes had to travel as quietly as possible to reduce detection. Noise analysis at sea revealed that certain propulsion units emitted faint tonal patterns that top-level hydrophones could detect under ideal conditions. This prompted further refinement of motor components, bearing lubrication, and blade design. We conducted extended vibration and sound profile testing, adjusting tolerances until the acoustic signature decreased. These improvements contributed to safer and more effective naval missions. During this period, intelligence officers occasionally briefed us on how enemy forces adapted their defensive tactics. Anti-submarine strategies evolved rapidly. Ships used new patterns of sonar scanning, and some deployed protective measures that required torpedoes to maintain stable depths for extended periods. This information guided modifications to depth-keeping mechanisms. Engineers enhanced pressure sensors and improved the calibration of hydrostatic valves. The result was a more consistent depth profile, an essential factor in long-range performance. Throughout Chapter 9 of my time at the factory, each new challenge taught me that developing advanced torpedoes required a balance of confidence and humility. No blueprint was final, no design immune to revision. Every improvement created new questions, and every test, whether in controlled facilities or open water, added another layer of understanding. The sea had a way of revealing truths we could not foresee. It never cooperated out of convenience. It exposed weaknesses with impartial precision. Despite these challenges, our program showed remarkable progress. Reports from operational missions began to mention enhanced reliability and improved consistency. the torpedoes reached their targets more predictably, extended their range with greater efficiency, and maintained stability under varied conditions. While much of this success belonged to the engineers, scientists, and sailors who contributed to every stage, I felt honored to know that my work played a part in these advancements. In the quiet hours after reviewing test logs or holding recovered components, I often reflected on the partnership between man and machine. Each torpedo represented thousands of collective decisions. Every bolt tightened, every measurement recorded, and every calibration completed with care mattered. The ocean remained unforgiving, yet we learned to work with its demands rather than against them. Chapter 9 taught me that the sea spoke in data, in currents, in temperature swings, in pressure variations. Listening to it required patience, discipline, and the understanding that progress came through constant adaptation. Our responsibility was to interpret its lessons accurately and to honor the trust placed in us by those who would depend on our work beneath the waves. I never imagined that the final days of my service inside the British long-range torpedo program would stay with me for the rest of my life. By 1945, as Europe entered its last and most fragile months of conflict, the factory where I had spent years hidden behind layers of official secrecy had become more than a workplace. It was a symbol of the silent, unseen efforts that kept the Royal Navy supplied with the technology it needed to survive. For years, we had lived at the crossroads of engineering and national responsibility, bound by rules that prevented us from speaking openly, even with our families. Now, in the twilight of the war, I felt the need to record everything before those memories faded. Within the walls of that factory, the atmosphere was changing. The urgency that had once pushed us to test torpedo propulsion systems around the clock had shifted into a tense waiting period. Reports indicated that German U-boat operations were being gradually suppressed due to improved Allied tactics, long-range patrol aircraft, and radar advancements. Still, no one in our facility allowed themselves to relax. We understood that even in the final months, a single gap in production or quality control could put naval crews at risk. Every torpedo could be the difference between a ship surviving or never making it home. Technicians around me had begun to reflect on the work we had done. We had produced the earliest long-range versions of the British 21-inch torpedoes designed for surface vessels and submarines, focusing on consistent propulsion, stable depth-keeping, and reliable guidance mechanisms. Our models were not guided in the modern sense. They used gyroscopic stabilization and compressed air systems that required absolute precision. Any flaw, even the thickness of a valve, or the alignment of a shaft, could cause a malfunction. My role had always involved testing the propulsion chambers, ensuring the turbines met the required revolutions without overheating or creating instability. The responsibility weighed heavily on me, especially in those last months when mechanical resources were stretched and replacement parts were harder to obtain. One morning, we were summoned to a meeting inside the secure conference room where the walls were thick and the windows reinforced. A senior officer from the Admiralty had arrived. His presence alone told us that something significant had shifted. He carried a folder marked under the highest level of wartime classification. When he spoke, his voice was firm, yet carried an unexpected sense of relief. He told us that our long-range torpedoes had played a decisive role in cutting off supply lines used by enemy submarines across the North Atlantic. He explained that several key operations, whose details we were not permitted to know, had succeeded because the equipment produced in our facility functioned exactly as required. For years, we had worked without knowing the real impact of our labor. Hearing it now, even in a limited form, created a moment of collective silence. Although we could not speak freely outside the room, it was the first time any of us felt our efforts recognized beyond routine inspection reports. I remember looking down at my uniform and thinking how strange it was that I had spent years in service without ever firing a weapon or stepping onto a ship engaged in combat. Yet our contribution was no less real. Naval warfare depended not only on the bravery of sailors, but also on the accuracy of the equipment built far from the front lines. That realization settled into me with quiet force. As the war neared its end, our factory began winding down its highest intensity shifts. Production continued, but the pressure that had once demanded constant acceleration was easing. Departments that had operated under a strict layered access system were now collaborating more openly in preparation for peacetime procedures. Still, secrecy remained. We were reminded that most of what we had learned inside the facility would remain classified for years, if not decades. Even after the conflict ended, we were not free to discuss technical details, internal structure, or operational methods. The world outside had no idea that a concealed factory on British soil had produced weapons vital to long-range naval missions. For a long time, no one would. My final day in the facility arrived with an unexpected calm. I completed my last inspection of a propulsion unit, signed my name on a log that would be stored in archives inaccessible to almost everyone, and walked through the workshop where I had spent so many hours listening to the rhythmic pulse of testing equipment. I knew every corner of that place, every echo the metal walls produced, every subtle vibration that signaled whether a chamber was functioning correctly. Leaving it behind felt like closing a chapter that had shaped me more than I had ever admitted. Decades later, when restrictions finally eased and I was allowed to speak publicly, I realized how much had been hidden from ordinary historical accounts. The story of that factory was not only about machinery. It was about the people who stayed committed to precision during a time when mistakes could cost lives. It was about scientific advancement pushed forward by urgency, yet controlled by discipline. It was about teamwork among individuals who rarely received recognition, but whose efforts helped shape the conflict's outcome. Now, as I recount all of this in my later years, I finally understand the weight of the silence we carried. The factory existed to safeguard the nation, but it also formed a generation of technicians, engineers, and servicemen who learned that duty often meant working in obscurity. By revealing the truth today, I am not seeking praise. I only want the story to be preserved. The work we did inside that hidden facility was part of a larger effort that helped secure the seas during a critical moment in history. And now that I am free to speak, I feel a responsibility to ensure it is not forgotten.